Okay. So we talked about entropy. I get my enthal and entry mixed up. Entropy, and now we're going to introduce that G, Gibbs free energy. And we're going to talk more about spontaneity. So this is like a review slide. Spontaneity, hopefully you kind of conjure up an image of spontaneous, just means it happens. So we said that Mother Nature tends to like things that are, oh, see, now I see how it's, well, you can't see, but my thing's not working right. It tends to like things that disperse energy and disperse matter. Now, which one of these dispersing energy, dispersing matter has to do with what we talked about Wednesday? Entropy. What do you think? Entropy is the dispersion of what? Matter. Very good. Yep. And so an enthalpy is the dispersion or not of energy. Let's see if this works. I don't know if I have the patience for this one, but we'll see. Okay, so the dispersion of matter, yep, entropy. The dispersion of energy, possibly enthalpy. And so actually it's a battle between change in enthalpy and change in entropy that kind of go together to make actually this G, this Gibbs free energy that we're introducing today. Oops, and it's not writing there, but it is there. Okay, so let's see what that looks like. First off, when we say something is spontaneous in terms of system in equilibrium, that means it's going to go from the left to the right on its own. Okay, that's spontaneous. I'm going to put an R over here and a P over here. Of course, that's reactant going to form products, which a chemical equilibrium, I think that's kind of interesting because, dude, the products go back to form reactants. It's like an equilibrium. But the fact that one arrow is longer than the other means that it's not an equilibrium, that it's favoring actually the product side. So it has to go from the left to the right in order to reach equilibrium. That's a spontaneous process. So non-spontaneous would look like this, where non-spontaneous means that actually, if it's potentially a chemical equilibrium, it needs to go back to back to reactants from products to reach equilibrium. Does that make sense? That's kind of how I think of it. And the next slide is going to tell you one of the things about chemical equilibria is we can just swing them around the double arrow. So if your reaction is not spontaneous, this is my like duh. If it's not spontaneous, just swing it around the double arrow and voila, you have it spontaneous. If it's not spontaneous, as written from left to right, switch reactants and products. Okay? Not sure what that is. We're going to ignore it. I have been all morning. Okay, so again, this is a review slide. This is the same slide as we had before. If we're interested in spontaneity, I love the word spontaneity, spontaneity, we need to look at what's going on with regard to the dispersion of energy and or the dispersion of matter. Okay. So, entropy, now I gotta concentrate, that's the S one, right? So let's make sure we're all on the same page with regard to changes in entropy, okay? And changes in enthalpy will be the energy changes. I'm sorry. I feel like these slides, I keep saying the same thing over and over. So if you want to, in your notes, you know, change in energy, that's going to be our delta H. Change in entropy, that's going to be our delta S. And if you're like me, the whole positive negative thing, I have to concentrate still. You know, a negative, something exothermic, it's a negative delta H. Something endothermic, it's a positive delta H. And we'll get some practice at this. So in your homework, we talked about entropy increasing, becoming more disordered. That actually favors spontaneity because it's the dispersion of matter. Okay? So the dispersion of matter, if Mother Nature likes that, which she does, then if you have a positive delta S, positive change in entropy, then the system's becoming more ordered, and that will favor spontaneity. If you have a negative change in entropy, that means you're doing some housekeeping. Your matter's becoming more organized. Okay, that means disorder is decreasing. It's becoming more ordered. And so, like at the top here, sometimes just to kind of review what this is. This would favor spontaneity, and this would disfavor spontaneity.
So how is it when the delta S is greater than 0, would that be exothermic?
No, it doesn't have to, it could be either way.
It could be either, okay.
Yeah, it could be either way. So the delta S is just the matter, and the energy is the delta H. So they're two different. And here in a minute, we're going to have one equation. It's kind of a simple equation that just adds those two together, basically. Yep. So here's our delta H's. So again, Chem 1, we talked about positive delta H's, that's endothermic, right? Yeah. And negative delta H's are exothermic. So which one of these favors spontaneity?
The exothermic one?
Yep, this exothermic. So this favors spontaneity. And so this must disfavor spontaneity. Yep. Yep. And here in a minute, and actually I could have done it before, but I'm going to have a slide that kind of looks at these, revisits the same ideas. And so you would call this one negative, right? And you would call this one positive. That's what the less than 0 means. That's what the greater than 0 means. Okay. So on to the G. So we had an H, we added an S, and now we have a G. G stands for Gibbs free energy. And I think in biology they use it more than I'm just going to use it, but it is a good check for what we call spontaneity. It's a good check to see if your reaction will go as it's listed from reactants to products to reach an equilibrium. So Gibbs free energy. It's a state function, which means it's independent of path. The opposite of state function would be path dependent. So in other words, it doesn't matter how you get from initial to final with regard to the Gibbs free energy of the system. Don't care about the path. You just care about the final and the initial conditions. So like this says, we're going to use it to test for spontaneity. Spontaneous spontaneity. Yep. So here you go, as promised. So Gibbs free energy then looks at both what is going on with regard to energy, that's your delta H term, and what's going on with regard to matter, that's your delta S term. Let's see, so this is energy, and this one is the matter. And so, let's see, how do I say this? So on your final exam, like, on your final exam, I will have an equation sheet. And I will give you, along with the sample questions on Monday, I'll give you that equation sheet that you're going to have for your final. And this will be on there. You just need to know how to use it. So notice we said that we were looking for negative delta H for it to be spontaneous. So if you kind of apply that to this, does this make sense that actually if delta G or Gibbs free energy is negative, we're gold with regard to spontaneity? Now notice it's delta H minus the temperature, and that's going to have to be in units of Kelvin, the absolute temperature times the change in entropy. And so a positive entropy change is a good thing for spontaneity. Notice actually we're subtracting, we introduce a negative there. So that all works. So if Gibbs free energy is negative, then and it's taking into account the change in enthalpy and entropy, then it's spontaneous as written. I just think that's funny that it's spontaneous as written. You're like, well, what's the big deal? You just swing it around the reaction arrow, and then it's spontaneous. If it's not spontaneous, and then you get it spontaneous. So to kind of summarize, that's what we're looking at. Now, if Gibbs free energy is equal to 0, check this out. That means it's not going to go left or right. I mean, it's in dynamic equilibrium, so it is going left to right, but the rates are equal. Okay? So that means your system's at equilibrium. I don't know. I had to change this in my notes. Does your delta H say something different? Mine got weird. Okay, good. So I think I mentioned this. What's that?
The delta H is different. It says delta H change. It's system.
Oh yeah, it does say right. So it should be system. Yeah, I looked at it and I was like, yeah, it should be system. So one of the things we talked about in Gen Chem 1, and to me it's kind of a subtle thing, but the Q is equal to MC sub P delta T, that sort of thing, that if it's happening at constant pressure, okay, then Q is equal to delta H. And so actually that's kind of what's being shown up here. So the change in entropy, oh yeah, see, now here's the catch, and actually I'm going to show you why this is. The caveat is it needs to be very near equilibrium. So your reaction arrows are equal length. At very near equilibrium, this is the situation. I have a little proof to kind of show you what that looks like. So if we go back, I'm going to try to show you why at equilibrium, that's the relationship. If they're at equilibrium, I told you that Gibbs free energy is equal to 0. If Gibbs free energy is equal to 0, we can go ahead and solve that or rearrange that expression. And so the absolute temperature times the change in entropy is equal to the change in enthalpy. Then rearranging for the change in entropy is equal to the change in enthalpy divided by the absolute temperature. So that's kind of a proof of what you saw on the previous slide. So let's go back to this equation. Okay, so I've got 4 slides to kind of talk you through the 4 different possibilities here. And again, if your idea is to test for spontaneity, that's what we're going to do. Does this make sense? If you are favoring spontaneity with regard to your delta H term, that means it's negative. And if you're favoring spontaneity with regard to your delta S term, that means it's positive, which is what I'm showing you here. Then, by golly, you can't help for the Gibbs free energy to be negative. That just will. Mathematically, it has no choice. Of course, that means that your reaction, your equilibrium, will proceed from left to right, as it will be spontaneous. Okay, so there are 4 choices here. That's the first of 4. Let's say, instead, that it favors spontaneity with regard to the delta H. It's negative. It's dispersing energy. But look at the delta S term here. We're going to make it negative. Okay, this is our second of 4. Now, a negative delta S means it's becoming more ordered, which disfavors spontaneity. So you still have a couple of options here, but it will be spontaneous if that enthalpy term, which is right here, if the enthalpy term is greater than the entropy term. Specifically, the absolute value, it needs to be larger than, the absolute values need to be, have this relationship. Okay, so if that is the case, if it's spontaneous, if your Gibbs free energy is less than 0, in this situation where you have it basically favored spontaneous with your favored spontaneity with your enthalpy term, disfavored spontaneity with your entropy term, then by golly, we say it's enthalpy driven. Too many E's. It is enthalpy driven. It won out. Now, do you guys buy this, that won't necessarily be the case? Because like this says, if your temperature is too high, if your temperature gets very high, look what happens here. This absolute value of the temperature times the entropy will be larger than your delta H. In that case, if temperature is too high, you're going to end up with a positive delta G, and it won't be spontaneous. Okay, so that's the second of 4. This is the third of 4. Well, let's just say that it's endothermic, so you have a positive delta H. And we're going to say here that actually it's the dispersion of energy, so you have a negative, so you have a positive delta S. So your delta S term favors spontaneity, but your delta H term disfavors spontaneity. Well, you could go ahead and have a spontaneous reaction. Your Gibbs free energy could be negative. If now your enthalpy term is less, so if your enthalpy term is less than your entropy term, and if you are successfully spontaneous, as indicated by the negative delta G, we say that it is entropy driven, okay? So enthalpy would have had otherwise, but entropy won out. And this will actually be favored at high temperatures.
This is probably, but so entropy is like chaos, enthalpy is energy.
Right.
Okay.
Yep. Yep. So this is going to be the case if your temperature's high. If your temperature's too low, then this will not, this inequality won't work for you. Because if your temperature's too low, then your enthalpy term is going to be greater, absolute value of it, and then you're going to end up with that one disfavors spontaneity. Everybody's tired today. So that was the third of 4. This is the last one. This is probably my favorite one. So in this one, we have a positive delta H, which means it's endothermic, and we have a negative delta S, which means it is creating order, a negative delta S. So you're like, dude, you basically have favors non-spontaneity, favors non-spontaneity. So in this case, for all cases, your Gibbs free energy is going to be positive. You can never get a negative delta G out of this situation because both terms are working against you. We never, ever, makes you want to go out and find one, right? Never be spontaneous. But how do you make it spontaneous? Yep, just flip it around.
So even if you flip this around, it would be spontaneous then?
Right. Yeah. So if you ever bump up something that's non-spontaneous from left to right, it's just written, just flip it around and then it's spontaneous. I just think that's fun. So the 4 scenarios, I don't think they're listed in order. Maybe they are. Yeah, they're listed in order. So the first scenario we looked at, it's got to be spontaneous because both the delta H and the delta S favor spontaneity. The next one, it can be spontaneous, but your delta S is going against you, okay? And we said that spontaneity would be favored at low temperatures. Okay, so that was the second scenario. Third scenario, this guy's going against you. This guy was going against you here. And so if it is spontaneous, we say it is entropy driven. And here, these guys both disfavor spontaneity. So that's kind of how that works. All right. So I think we're bumping up against a calculation. Are we? So this is one way to calculate Gibbs free energy. So this will be on your sheet. But there's another way to calculate Gibbs free energy. And if you did the homework, wait, did you guys have to do these? No, you didn't, did you? Okay. But this is the formula we looked at with entropy. You can come up with delta S this way. You can come up with delta G this way. And so basically what it is you know all the, this is what F means of formation. We have the standard molar enthalpy of formation. This little F means of formation. So this is the Gibbs free energy of formation of each one of the products. It's always final minus initial. You add those up together. What's this A?
Yeah.
Yep, coefficient. Yep, that's your coefficient. And then you sum up of the reactants, and then you can get the overall Gibbs free energy of the reaction. So, yeah, the F means formation. The little knot we said means standard conditions, which is 25 degrees Celsius, 1 bar pressure. Okay. Yeah, we're going to talk a little more about standard states, standard conditions, well, standard states. The other day, or Wednesday, I said we'd be using it. I don't think we will be using the whole absolute zero, like what do we say, the entropy of a substance in its pure crystalline state, and absolute zero is 0. But we will be using this one. What this one says is that the standard Gibbs free energy of formation, standard means it's at 25 degrees Celsius, for an element in its standard state at standard conditions is 0. Okay, so we will be using that one. So case in point, that last little bit I said we will be using those, like hydrogen gas. Well, hydrogen anyway, at 25 degrees Celsius is a gas, okay? And so notice its Gibbs free energy of formation is 0. Check this out down here though. We've actually got, do you remember we call them allotropes? There are like 3 or 4 different allotropes of carbon. We have the graphite, diamond, maybe there's just 3, and the buckyball, maybe that's just 3. But the standard state is it's graphite. So it's the Gibbs free energy of formation of carbon in its graphite state is 0. So we're going to be using these, I think, to work the next problem. Okay. So it's always products minus the reactants, the summation of. So we're going to actually use those, it's called thermodynamic properties, the delta H, the delta S, and the delta G of these things to knock these out. So once we have delta H, we can, going back to Gen Chem 1, say whether it's endothermic or exothermic. Once we have delta S, we can say whether it's becoming more ordered or disordered. And then once we have delta G, we can say something about its spontaneity. So this is just kind of summary of, this is kind of a different way to look at it. Notice I have all the pluses lined up and all the negatives lined up. So let's just go across here. Let's start with this one. So for, bless you, enthalpy, which one of these favors spontaneity? Endothermic or exothermic? Yep, exothermic favors spontaneity. Okay, on this one, how about entropy? Plus entropy or negative entropy favors spontaneity? Plus, yep, very good. And most recently, we've linked the delta G to is equal to delta H minus T delta S. So which one of these favors or means it's spontaneous? The last one is spontaneous, yeah. Okay, very good. Okay, so this isn't even a subtable of the table we looked at before. We're going to be using these first 2 columns, okay, to knock out the change in enthalpy of the reaction, the change in entropy of the reaction, and then actually we're going to use those 2 deltas of the reaction to knock out the delta G of the reaction. But we could have returned back and used this column. So let's see what this looks like then. Remember, this sort of problem, you're going to have to show over your work, especially on your final exam if it's one of the last questions. And it's easy to get mixed up. So I like to kind of separate the products from the reactants. So it's the summation of the products first. So we have to use the stoichiometric coefficients in the balanced equation. So the coefficient from the CO2 is 1, so 1 mole of CO2, and the standard enthalpy of formation is negative 393.5 kilojoules per mole of CO2. Then we need to look at the other reactant, 2 moles of H2O, times its standard molar enthalpy of formation, negative 285.8 kilojoules per mole of H2O. Rounding it to 1 decimal, you get a negative 965.1 kilojoules of energy. So that's the product side. So it's products minus reactants. The reactant side, oops, yeah, I think I said that wrong. But the reactant side looks like this. We have methane and O2. So 1 mole of CH4 from the balanced equation times its standard molar enthalpy of formation, negative 74.8. Don't know what that extra decimal is doing in there. Bonus decimal. Kilojoules per 1 mole of methane, plus 2 moles of CO2, because the coefficient in front of the O2 is 2. And this is where, you know, you get, since O2 is in its gaseous state, that's its standard form at standard conditions, so we could have already said that was 0. Sometimes students say, well, Mrs. Snipes, do I have to introduce this term if I know it's going to be 0? I'd be like, well, leave it out at your own risk. So anyway, negative 74.8 kilojoules. So we're going to take the top number and from that subtract the bottom number. The reason I like doing this is because now you're like, okay, a negative, so subtracting a negative, that makes it positive, doesn't it? It's really easy to mess up your signs here. So we get the change in enthalpy of the reaction is negative 890.3 kilojoules. So how many people think that this is endothermic? How many people think it's exothermic? Me too. Mike was busy writing. Exothermic. So how many people think this favors spontaneity? How many people think this disfavors spontaneity? How many people don't know? So Mike, explain. Why does it favor spontaneity?
Because delta H is negative.
Because delta, well, a little more, like,
Well, because then that is exothermic.
okay.
That's what I meant to say.
Okay, and exothermic, is that getting rid of energy or taking in energy? Yeah, so that's the dispersion part. That you look convinced. You don't quite look convinced yet, but okay.
I'll be convinced eventually.
Okay, so yep, since it's negative, the reaction is exothermic, and that will favor, favor spontaneity, but we don't know if it's spontaneous yet until we come up with the delta S term. There are 2 terms that kind of go into that delta G. Okay, so let's look at the delta S. So the product side, 1 mole of CO2 times its, bless you, times its entropy per mole, molar entropy, I guess, 213.7 joules per mole Kelvin. Now, if you're like me, you're like, oh, dang, our enthalpy was in kilojoules, and this is in joules. So you're right, we're going to have to fix that when we add them together. Plus 2 moles of H2O times 69.9 joules per mole Kelvin for water, for H2O. So those numbers, of course, came from the table a little bit ago. So that means on the product side, we have an entropy of 353.5 joules per Kelvin. So on the reactant side, it looks like this balanced equation. We had 1 mole of CH4. From the table, its entropy, molar entropy, is 186.3 joules per mole Kelvin. Plus we had 2 moles of O2, and its molar entropy was 205.1 joules per mole Kelvin. And that gives us 596.5 joules per Kelvin. So we're going to take the first number and from that subtract the second number. So it's looking like a negative delta S, isn't it? So the delta S of the reaction, it's products minus reactants. So we got 353.5 minus 596.5, and the units would be joules per Kelvin. So you're looking at a negative 243.0 joules per Kelvin. So can you look back a few slides? What do you think? We're going to have to find a temperature to use in that equation. What is our temperature? It is 25 degrees Celsius. Yeah, and I'd have to double check. I think it might have said it's standard temperatures. I'm not sure. So very good. Can we use 25 degrees Celsius? Right, that you got to convert it to Kelvin. Yep. Okay, so it's negative. So delta S negative means it's creating order. So does this favor, or just how many people think this favors spontaneity? How many people think this disfavors spontaneity? Why does it disfavor spontaneity?
Why does it disfavor spontaneity? Because it's creating order.
Right, it's creating order. And it's the opposite of the dispersion of matter. Yep. You'll get it too. Yeah, I'm not, like I know I've told you, but I don't memorize things very well. So I just try to kind of go back to what I know about spontaneity favors dispersion of both matter and energy. And then I go back to what does negative delta S means. Well, it means becoming more ordered, which is the opposite of dispersion. So now to get that last one, we could go back to the raw G's, but we're going to go ahead and use this equation instead. So we have a delta H, we have a delta S, and you told me the temperature was going to be 25 degrees Celsius. So these are actually just kind of reviewing the numbers that you already wrote down. We came up with delta H is negative 890.3 kilojoules. Delta S is negative 243.0 joules per Kelvin. Now again, we're going to have to make those kilojoules and joules agree. And you could go either way as far as I'm concerned. Okay, but they need to be uniform. Yep, and our temperature is 25.0. I'm not sure why I didn't go 25.00, and then we could have kept 2 decimals for the temperature. I don't know. I guess I kind of do know. I've said that whenever you're working with this, you guys probably buy this. This is like a constant. Well, kind of a constant. It's a constant offset to get from units of Celsius to Kelvin. You never want to do a little tiny problem like this and end up with something you're going to use in your problem, which is temperature, that's going to limit your rounding. Up here, I'm liking 4 sig figs here, 4 sig figs here. So we need to have at least 4 sig figs here, at least. If we had gone with 25, okay, plus 273.15, okay, we'd have to round to the nearest ones place. So that would just give us 298, and that was 3 sig figs. So you don't want to do that. So to get at least 4 sig figs, that's why, anyway. So we're ready to go ahead and apply the delta G is equal to delta H minus the absolute temperature times delta S. Did I say that right? Delta H minus the absolute temperature times delta S. So you can kind of see what I've done over here is for the T delta S, I've gone ahead and introduced, where's my cursor? I've gone ahead and introduced one more term here to go ahead and get from units of joules of energy to kilojoules. Okay, so here's our delta H, and here is our T delta S, and then that's to just kind of fix it. So we don't do a lot of subtraction in chemistry, but here we are. So to me, I may not know what that entropy term is, but by golly, I know enthalpy is to the nearest tenth. That's what I'm going to go with. Okay. So the delta G, Gibbs free energy for this reaction is negative, dun, 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 817.9. And notice that when we did these three terms over here, our units of Kelvin cancel. Isn't that fun? Like it should. Our units of joules cancel, we have kilojoules, which is wonderful. Okay, so how many people think this is spontaneous? We have a consensus there. Yep, it is spontaneous. Good job. Okay, it's a lot of work to see if it's spontaneous or not. Okay. But do you buy this? Because this could be like a follow-up question. When we looked at, when we looked at the enthalpy and the entropy, we said that the enthalpy being exothermic, dispersion of energy, favored spontaneity. But we said the entropy being negative, forming more order, actually disfavored spontaneity. So the fact that the delta G was negative means not only was it spontaneous, but it was driven by the enthalpy, the delta H term, not the delta S term.
So when you're going through, whichever the one is that favors the spontaneity, that's what drives it.
Yep, that's the driver. Yep. If it is successfully spontaneous. I mean, if it fails to be spontaneous, then
What if they both favor it? Then what's
if they both favor it, then there's no driver. That's just, yeah. You just know it's got to be spontaneous if it's exothermic and becoming more disordered. Yeah. No driver there. Okay, let's do another problem. Actually, I'm going to work them down here, which is I'm going to kind of do a shorthand working, which some of you guys probably really like. But this, all we're doing is dissolving ammonium nitrate. You can tell that. So, get your Gen Chem 1 skills going here. The phase it's going from aqueous means dissolved. So we're going to actually look at some thermodynamic data, and we're going to knock out the enthalpy, the entropy, and the Gibbs free energy associated with this. Now, this isn't a chemical reaction, I don't think. Not new substances are not formed. It's more like a physical process. Okay, so with the delta H, we'll see is it endo or exothermic. With the delta S, we'll see is it becoming more ordered or disordered. Right off the bat, what do you think about the delta S term? How many people think it's becoming more ordered? How many people think it's becoming more disordered? I got 2 to disordered. Yeah. It's becoming more disordered. So that would favor spontaneity, but let's see what the enthalpy term does. So this is the data we're going to use. This is the thermodynamic constants, table in the back of your book. This is where I said I'm going to kind of do it. It's kind of shorthand, but it's always products minus reactants. So I'm going to go up here at the top here, and I'm going to put a product. It's going to be products. That's my product minus my reactant. Okay, so it's really easy to screw this up. So you see what I mean? I'm kind of going quick and dirty since it's like the stoichiometry is 1 across the board and I'm only dealing with one species on either side of the reaction arrow. I'm simply taking the enthalpy of the product. Oh, where's my thing go? The enthalpy of the product. Okay, and from that subtracting the enthalpy of the reactant. Okay, so what do you think? Is this endo or exothermic? It is endo. So endothermic, is that dispersion or coming together of energy? Coming together, yep. Energy being put in. So does it favor or disfavor? What?
Favor it?
No. No, because Mother Nature wants to push out energy and wants to push out matter. So coming in means it disfavors spontaneity. But thank you for answering. Okay, endothermic. Okay. So let's look at the entropy term, and we'll do a similar thing. We're going to take the 259.8 kilojoules per mole Kelvin, and from that we're going to subtract 151.1 joules per mole Kelvin. And we come up with a positive 108.7, that would be units of joules per Kelvin. So is this becoming more ordered or disordered? Disordered, because it's positive. Disordered. And when you think of disordered, what do you think? Is that pushing out energy or energy coming in? Dispersing energy. So does it favor or disfavor spontaneity? It favors, yep. So I'll put a little smiley face here for this favors spontaneity, and I'll put a little frowny face up here that does not favor spontaneity. So the last one, and I think I'm going to do it this way instead of the other way. I'm not going back to the temperature thing. So we said that we can take the products minus reactants. So products minus reactants, so the negative 190 minus 6 minus a negative 183.9, those units are kilojoules. So we get a negative 6.7 kilojoules. So how many people think this is spontaneous? Yes, it is spontaneous. Ding, 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 ding. Yep. But do you buy this, that it's spontaneous, but we can say something about it being driven? I should have asked you which one you think it's driven by. But does this make sense? It is entropy driven because the enthalpy term went against it and the entropy term went for it. And since it's one out, yep, you got it. I mean, you can look at the, yeah. What's that?
So this slide has a lot to write.
Okay, thanks. Am I to assignment slide?
Next one is,
Excellent.
Liar, liar, pants on fire. I did pick one of these problems, it's in consolation, that you can earn 10 extra credit points good towards assignments, missed assignments if you want. Yep. So do you have 23, 24, 25, 26, and 27 will be worth 10 extra credit points. But let me show you 27 before I get too happy. So yeah, I'm using a different approach, so we'll see if this works for me. Let's see, I need to change my pointer to a arrow. Okay, so this is the old. This is what you're used to. So these will be pushed out under Twitter. And like usual, if I don't push them out on Twitter, you know, let me know. So I don't have any builds here, but the first problem looks like this. It's kind of familiar. You know, I definitely think you can do something with that. That's 23. 24 looks like this. And in this case, you're going to use that summation. So yeah, there's quite a few here. Now, if you're like, I'll tell you a secret. So like, so to me, there's like 4 problems that are very similar. So to me, if you're in a time crunch, at least do the first 2, and there's a good chance I won't even know that you didn't do the other 2. Okay? I bet it's the end of the semester. I bet I'm not alone in that. For this one, it's a unique one, so you want to do this one. I kind of gave some hints there. And then it's just and then 26 is the same as 25. And then this is the extra credit one. I know, and it's fun though. If you like Hess's Law, you'll like this problem. So, yep, so I'll push all those out there. Any questions? Very good. Well, everybody have a great weekend.